Hi guys, welcome to the channel. Hope you all are doing well. In case if you are new to the channel, then please subscribe the channel in case you haven't done so. And I would request that, I always request that you do not follow a particular video. Please go through the links of the video in the playlist. Only then probably you will be able to follow my videos and the coming lectures. So we are just continuing with the kinetic theory of gases today as well, kinetic theory of gases, and this would be the end of kinetic theory. I mean, we'll be starting with a new topic in the coming videos, and the last topic is Stefan Boltzmann's law of radiation. So Stefan Boltzmann law of radiation is very simple. It just says it is applicable to black bodies, but with a small tweak from here and there we can apply this for ordinary body as well. So we can apply this for ordinary body as well, but right now in the original version it is for black body. Now what does it say? It says that the amount of heat energy emitted per unit area per unit time, so it should be in the denominator, it is per unit. So the amount of heat energy emitted per unit area per unit time for a black body is directly proportional to the fourth power of the absolute temperature. So very simple, just you can repeat it with me. It says that the amount of heat energy emitted per unit area per unit time for a black body is directly proportional to the fourth power of absolute temperature. So the amount of heat energy emitted per unit area per unit time is directly proportional to the fourth power of absolute temperature for a perfectly black body. So that's what I have written. The amount of heat energy emitted per unit area per unit time for a perfectly black body is directly proportional to the fourth power of absolute temperature. So that's what mathematically we have written. So if you can see, Q upon AT is directly proportional to fourth power of absolute temperature. So Q is the heat emitted by that body, A is the area, T is time, and capital T is the absolute temperature. So absolute temperature means temperature in Kelvin. Okay, now in order to remove this proportionality sign, we'll remove that proportionality sign and multiply by a constant, and this constant is written as sigma. This is sigma. Okay, so this is what is called as sigma in Greek, and this sigma is what is called as the Stefan's constant, and Stefan constant is 5.67 into 10 raised to minus 8 joule. Now units will see how it works, but the constant for Stefan's constant is very easy to remember. If you see 5, 6, 7 and there is an 8 over here, so 5.67 10 raised to minus 8, that makes you to remember makes it easier to remember sigma, that is Stefan's constant. Now if you see this equation, this particular equation, then sigma can be written as Q upon AT T raised to 4. So if you see this sigma is equal to Q upon AT T raised to 4, then energy is written as joule, area is meter square, time is second, and temperature is Kelvin raised to the power 4. So that's why joule per meter square second Kelvin raised to 4 becomes the unit. And you all know that power is energy upon time, that is work upon time. Power is nothing but energy upon time. So power is watt, energy is joule, and time is second. So what is equal to joule per second? This is not a question, this is just a way of saying what is equal to joule per second. So what is the unit of power? It's watt. Okay, it's watt. So wherever there is a joule and there is a second, joule per second is written as watt, meter square as it is, Kelvin raised to 4 as it is. So you can also write as watt per meter square Kelvin raised to 4. Now if you see this q by at, if you follow my previous lectures, you will find out this is nothing but called as the emissive power. Now this emissive power of a black body is written as B, and for an ordinary body it is written as E. So because this is applicable for black body, I am writing as EB. So q by at is written as EB, sigma is as it is, T raised to 4 is as it is. So this becomes the Stefan Boltzmann's law of heat radiation, and this is applicable for black body. But yes, in regular life we are not going to find out black bodies, we are going to find out ordinary bodies. So we'll have to manipulate this equation for ordinary body. So it's very simple, you just move it like this. Also E is equal to, now this small e is called as the emissivity or the coefficient of emission. Now this also we have discussed in previous videos. In case if you are not following this part, I would request you to just go back 2 to 3 videos and you will find out the proper definition of emissivity. It is also called as coefficient of emission, and it is the ratio of emissive power of an ordinary body to the emissive power of a perfectly black body. So E is emissive power, but this is for ordinary body, and EB is emissive power, but this is for black body. Okay, and if you take the ratio of these two, you get coefficient of emission, which is also called as emissivity. So you just move this EB on the other side and this E on the denominator, so you get EB is equal to E upon E. Now EB would be E upon E. So now if you see, this is EB and you just replace this value over here, so I get E upon E is equal to sigma as it is, T as it is. Now just move this E on the other side, small e on the other side, so you get E is equal to E sigma T raised to 4, which is an Boltzmann's law for an ordinary body. So if you see, there is a difference of only an E, like there is no E over here and there is a small e over here. And if you recollect from my previous class, then you will realize that I have said for a perfectly black body, small e, that is emissivity ka value is 1. Small e, that emissivity ka value is 1. So if I put over 1 over here, then it becomes the emissive power for a perfectly black body. So for an ordinary body it is E sigma T raised to 4. For a perfectly black body it is EB is equal to sigma T raised to 4. So this is for perfectly black body and this is for ordinary body. So this marks the end of this Stefan Boltzmann's radiation law. But however, there is a small addition to this kind of this formula, and that is loss or gain of heat. Let's see what it is all about. Just focus on the laser marker where I am trying to show you. Now let's say suppose this is one body which is hot and its temperature is T is equal to 80 degrees Celsius. And the surrounding temperature is T0, which is equal to 20 degrees Celsius. So there is a difference of temperature of almost like 60 degrees Celsius. Now because this body is hot, this is going to emit energy, that is heat. But as we have studied in Prevost's theory, that any body at any given temperature is going to emit as well as absorb energy, heat energy. So as this body is hot, 80 degrees Celsius, this is emitting as well as it will absorb as well. It is not going to only emit, it is going to absorb as well as emit as well, both. Now the rate of emission will depend on the body's temperature, and the rate of absorption will depend on the surrounding temperature, which is 20 degrees Celsius. So this body is going to emit more and absorb less. Now only when there is a thermal equilibrium, like both temperature comes and settles to like 25 degrees Celsius, that time we can say that the body is in thermal equilibrium with the surrounding, and then the rate of emission and the rate of absorption will become equal. But as of now it is not. So how much is the loss of energy the body is going to occur? Then that will be given by like this. See, the amount of energy emitted by this body would be equal to sigma T raised to 4. I am assuming that this body is a perfectly black body. I am assuming that this body is perfectly black. This body is perfectly black body. Okay, so this body is perfectly black body. Okay, so let's see how it works. Now, because this body is perfectly black body, I can say that the rate of emission or the amount of energy emitted per unit area per unit time, that is, I am applying a Stefan Boltzmann's law, I'll get something called as sigma T raised to 4. This is the amount of energy emitted per unit area per unit time. So that's the amount of energy. Right now you don't look at this. So the amount of energy it is emitting is sigma T raised to 4. This is the amount of energy emitted by this body. But at the same time it is absorbing this much amount of some amount of energy. Now the amount of energy which it is going to absorb will depend upon the amount of energy emitted by the surrounding. So you see, the surrounding is emitting the energy with a rate of 20 degrees Celsius. So I can say, okay, E is equal to sigma T raised to 4. This is the amount of energy emitted by the body. But E is equal to sigma T0 raised to 4. This is the amount of energy emitted by the surrounding. And this amount of energy which is emitted by the surrounding is going to get absorbed by the black body. So that's why. So the net would be sigma T raised to 4 minus sigma T0 raised to 4. I would again request you go slide the sig bar behind and understand my words, what I'm trying to convey. It's slightly tricky. This is the amount of energy emitted, this is the amount of heat energy absorbed, and if you subtract that, what you get is the loss or gain of heat energy by a perfectly black body. Now how does this sigma T0 raised to 4 is that where the most people confuse. This is the amount of heat energy emitted by the surrounding, and this surrounding emitted energy is being absorbed by the black body. Okay, so that's where that sigma T0 raised to 4 is concerned. I have taken sigma common outside, so I get sigma T raised to 4 minus T0 raised to 4. Now, in case if I want that for an ordinary body, this is for black body, this is for ordinary body, I just have to multiply an E over here. So if you see E over here, it's an ordinary body, that is E sigma T raised to 4 minus T0 raised to 4. So that's what it is. Now there is one last aspect. I have also written a gain. Why is that gain? Because let's say, suppose in case we have a body which is at a lower temperature, let's say T is equal to 20 degrees Celsius, and if we have a surrounding at a greater temperature, let's say 80 degrees Celsius, like a oven or a furnace, then your T raised to 4, your body's temperature is lower, and T0 that is the surrounding temperature is more. So in that case you will get a negative answer. Not a negative answer, but you will get a negative answer because T raised to 4 will be a smaller number and this will be a bigger number. So when you subtract it, you will get a negative number. So that way we say that the energy is gained when the body's temperature is lower and the surrounding temperature is higher. So body's temperature lower and surrounding temperature higher, that means we are going to get gain. So you just have to flip the formula. You just have to write sigma T0 raised to 4 minus T raised to 4. So this will be for gain. This will be for gain, because ultimately if the body's temperature is lower, it is going to gain energy from the surrounding. So that's why we just flip the formula from here to there. When the body is at a lower temperature and surrounding is at a higher temperature. So finally we are done with this topic, and we are winding up for today. And thank you so much for watching. In case you are not following any of the part of the video, I would really suggest you to go back to one of the previous videos or topics and just keep following. You will definitely get most of the things. Kindly subscribe the channel if you haven't done so. Also please comment, like, and also share to students or people who might find this knowledgeable videos interesting. Thank you so much. Bye.